Thank you, Ricard, for the introduction. And well, it was very nice introduction, and I'm very glad because now that you have done that introduction, I'm able to put in pictures what you just said in words. I have several pictures showing what you just said, the different sources of imbalance. For example, in this case, the imbalance is because of a partition of the data. In this case, it's because of the different computational needs. So the one that is taking longer has a lower IPC for some reason. This is a problem with the network or the MPI implementation, where the processes finish a collective call in this manner, producing an imbalance afterwards. And we also have our lovely noise, which can appear in hardware or software, noise and variations. So what we say is, so LeWI imbalance has been with us for quite a long time, since parallel computing appeared, I guess. And why it's not a solution yet? Because what you just said, that there are very different sources and we need different solutions. And for MPI in specific is quite difficult because you need to move data around, and moving data around is expensive. So what we try to do is to react when the imbalance is happening, as Ricard said. So what we say is that we don't try to fight the imbalance. So the imbalance is there and we cannot fight it forever. So let's adapt. Let's do like Bruce Lee and adapt to it. And the solution that we propose is the DLV library. The objective of this library is to address all sources of imbalance, if it's a fine-grained dynamic, and to react when it's happening. So we aim to provide a real product for HPC. So it's integrated with common programming models like MPI and OpenMP. And the idea is to be completely transparent to the application. It's a runtime library that you can use completely transparent. The idea behind what we do, I'll explain it with a picture that it's always easier to understand, and an example. So if we have an HPC application, and this application has two MPI processes, and each one of these processes can use two cores. There's a huge imbalance between them. So the first process is computing and finish the work faster. Then it waits in an MPI blocking call, while the other process is doing its computation. What we propose is when the first MPI process finishes its computation, he lends its two CPUs to the other MPI process running in the same node. This way, the second MPI process can use 4 CPUs and finish the computation faster. And here are the traces that I like to show to understand everything better. So you have seen several of these already in Ricard's presentation and my own, but let me explain a bit in detail what you can see in these pictures. In every line represents one thread, usually grouped by processes. So in this case, I have 2 MPI processes with 8 threads each one, this first process and the second process. And in the x-axis, we find the time. The color can represent different things depending on what we are showing. In this case, pink means computation, and red means communication, and black means idle, doing nothing. So we can see in this trace how the first process finished the computation first, and then it's just waiting for the second process. When we use DLV or mechanism LeWI, we can see how the second MPI process can start using more threads when the first one finishes, so that they can finish the computation faster. The iteration, in fact, finishes here and it starts the second one. So all this time is the one that we gain. How this works? Well, we try to be integrated with the different layers of the software stack, in special with MPI and OpenMP, but we also offer an API for applications, because we have, at the beginning, we try to be very transparent to the application, don't need to add anything, but at the end we have seen that the application developers are the ones that know best their application. So they can give us some hints and just mark in the code where they want DLV to start working, or when to do nothing, or things like that. So we offer an API for this fine-tuning, let's say. And as I said, we are integrated with MPI and OpenMP, so we can work out of the box with the most common programming languages. So in this this is kind of an introduction to DLV, but now I'm going to focus on all the work that we have done together with DLV and Alya. To start, one of the first things that we collaborated was this problem solving the respiratory system, the human respiratory system, simulating the air that was going through the respiratory system. And when we obtain trace, in this case, each color represents a different phase of the application, we could see the high load imbalance that appears here. Which are the steps that we need to use DLV in Alya? Well, as the load imbalance was so localized and we wanted to focus in this part of the code, we add calls to DLV enable and disable, here to enable DLV and here to disable it. This way, DLV will only be active in this part of the application. It will be disabled in the rest of the execution. As in Alya, it was already parallelized with OpenMP, this part of the code. We just needed to compile with Mercurium or on compiler, because we wanted to use our version of OpenMP, and then run adding support for DLV. We preload the DLV library. This way we can intercept the MPI calls, and then we set some environment variables to tell DLV how to behave. And these were some of the results that we obtained with DLV. The original execution with pure MPI was had this performance. The straight line is the hybrid version, which was not very good. That's why it's not usually used. They usually use the pure MPI one. And in the x-axis, we can see the different combinations of MPIs and threads to see which is the best configuration. And the dashed line is the execution time when using DLV. We can see that the gain was very good compared to the pure MPI execution, and also compared to the different hybrid versions. One of the nice things that we find out also is that the DLV is able to offer these like flat lines. So this means that it can get quite good performance independently of what the user decides to do, because this is kind of decision of the user, how to launch the application. This same experiment, we ran it in a high number of cores of Mare Nostrum. And we show that even if, because most of you are thinking now, DLV can only act inside a node. Yes, we can only balance within a computational node. We cannot balance between different nodes. But even acting only inside the nodes, we were able to obtain this speed up. Comparing the original version is the red line with DLV is the blue one, running in more than 16,000 processors. Another interesting input and test case that we used was a coupled one. This was also the respiratory system, but in this case, particles were also annihilated. So there were two physics that needed to be solved, the fluid and the particle. Alya can do this in two ways, the synchronous one, where first the fluid is solved and then the particles, or in an asynchronous way, where some MPI processes solve the fluid and other ones solve the particles. And then based on this, we said, okay, but there could be that the problem is fluid dominated, so there are few particles and most of the time it's the fluid, the one that it's running, but it can also happen that the code is particle dominated, that there are a lot of particles to solve, and the particles is the part of the code that takes more time. So that's why we will see different examples. This is so that you can have an idea of what we were facing. This is an asynchronous one with particle dominated. We can see that some MPI processes are solving the fluid and other ones are solving the particles. We see the load imbalance that we have seen before, and now we see the extreme load imbalance in the particles. And not only this imbalance is extreme at this point, because this is the beginning of the simulation. So all the particles are being innate and are in the same partition. But also this imbalance will be changing during the execution. So these particles will be moving around and will be in another domain some steps later. So at this point, when a user, scientist needs to launch this simulation, he must decide whether to use the synchronous or asynchronous version, and how many fluid processes and how many particle processes to use. And this is what we want to help also. To enable DLV in this simulation, in this case, the loop over the particles in Alya was not parallelized, so we need to parallelize that loop. And then we did the same. We enable and disable DLV around that loop. Also, in this case, as you can see, all the MPI processes that are solving the fluid are together, and the ones that are solving the particles are together. As we want to mix them, we use a round-robin distribution of MPI processes among nodes, because if not, if with a normal distribution, you will get all the fluid processes in the same nodes and all the particle processes in the same nodes. And now we zoom in one of the nodes, because if not, the traces are quite difficult to analyze. So now we are seeing one of the nodes, in fact, the most loaded one of the simulation. This is the original run, and this is what happens when we run with DLV. We can see here that DLV takes 3 actions. It's load balancing the fluid, so this time that was here now is computed here. We can see how it load balances particles. So in this node, there were 2 processes running particles, but one of them had no particle to solve, and now his CPUs can solve the second process. And finally, it load balances the 2 codes. So all this time that the fluid processes are waiting for the particles to finish, now they are helping the particles finish its computation faster. Now some numbers. These are the 2 experiments that we executed, where the fluid dominates the execution and another one where the particles dominates the execution. And the different columns in the x-axis, we see the different ways of running it. The synchronous ones, where all the MPIs run first, solve the fluid and then solve the particles, and the asynchronous ones. But in the asynchronous ones, we need to choose how many processes to use from each type. So that's why we see different bars with the different numbers of MPI processes per physics to solve. And well, we see not only that DLV obtains speed up over 2x for almost all the cases, but also that it's very different depending on the case. Of course, it depends on the amount of imbalance that there was in the execution, the benefit that DLV can obtain. But one of the most interesting things is the flat lines that I was saying before. Even the original bars have some spikes, DLV is able to offer a much more flat distribution. So let's say it puts less pressure in the user in taking the wrong decision. You can find more details in these experiments and that I'm showing in the papers that I'm showing at the bottom. And after that, we did an interesting use case also. This was a fluid structure interaction. There was a simulation of the aorta. And in this simulation, some processes are solving the blood, that it's a fluid inside the aorta, the velocity of the blood. And some other processes are solving the solid, which is the aorta per se, and they are solving the displacement of the solid. But these two physics, and unless the fluid and the particles in the example above, cannot be run at the same time. So first the fluid processes run, and then they send the velocity to the solid processes. Then the solid processes solve their physics, and again. So in this trace, it means that when they are in blue, all the processes are just doing nothing and wasting time. So in this case, we used another feature of DLB, what we call DLB barrier. For this, we add calls at some points to DLB barrier. So the tricky part here is to find these points. If you know the code well, should be quite easy. At the points where there are synchronization in the fluid and in the solid code. In this case, we don't need OpenMP nor ohms. We just use the DLB barrier. Because what we try is, this is the original run where all the blue was just wasted. And the first thing that we thought was, okay, if all the blue is wasted, let's do something. Let's run the solid processes in the same cores as the fluid ones, because they are not using the core at the same time. And this is what we tried in the second trace. But this, in fact, takes longer than the original one. Why this happens? This happens because MPI is much more greedy than what we think. So when MPI is waiting for a message, it's just not sitting there waiting. It's doing like the kids in the car. They are saying, is there a message for me yet? Is there a message for me yet? Is there a message for me? Is there a message for me? So they are in fact using the CPU. This means that they are bothering the processes that are trying to do useful work. So this was not useful, but MPI offers a wait mode that makes MPI calls really wait and do not use the CPU. We tried this version, and this is what we obtained. What was happening in this version? Why it was performing worse than the first one? What happens here is that in some parts of the execution inside of one of the physics, there's a high number of point-to-point communications. And these communications need to be very fast. So it was adding overhead to use this kind of MPI wait mode in this part of the code. And the last picture is when we used DLB barrier. With DLB barrier, we did the same. We put these processes running in the same cores as these ones, so they were sharing resources, but DLB was doing an intelligent sharing of resources, letting the CPUs to the physics that was doing really the work. More details on everything, because this is just the nice pictures, are in this paper here. And let me show one more example. In this case is the last one that we are working right now. It's quite new. This is a combustion use case. We are solving a Bunsen flame. And the problem with this simulation is that the chemical reaction only happens in some points, and this produces a huge load imbalance. And this is similar to the particles problems. This is something that we can not predict because it will change during the simulation. These are the changes that we needed to do to the code, because again, it was not parallelized with OpenMP, so we added a task loop. The good thing is that when you have some code that is very localized with just one pragma, we are able to parallelize it. So we parallelize it, and we add a call to DLB barrier at the end, ensuring that this way all the resources will be shared there, and we don't need to intercept all the MPI calls as we usually do, but that adds quite some overhead. And well, in this case, I don't have very fancy pictures because I've said the work is still in progress, but it's quite promising. these are the scaling that we are obtaining. The original one is the orange line. The ideal based on the original is the yellow. And the speed up that we are obtaining with respect to the original one with DLB is this. We are, in fact, going 2 times faster with up to this number of MPI ranks. Just by adding, as I said, the pragma, the DLB barrier, and that part where you intercept the MPI calls that I said at the beginning. And that's just to summarize. DLB, we just released the version 3 last December. We have 3 different modules. The one I have been focusing today is LeWI. And you can download it free from this website. And well, we are also, as Ricard said, we are also part of POP, and you can ask us for a performance audit. And if you have, if you think you have a load balancing problem, we can analyze it and tell you if it's a good target to use DLB. And then sometimes we can even provide a proof of concept within the project to test how DLB could work in your code. And that was all from my side. I don't know if you want to continue, Ricard, or...
The same SFC all the time. The load balancing is related with tuning the splitting points of the SFC, right? And we like to, the idea is to do this repartitioning at runtime because in complex problems, we generally have seen that the weighting, basing the partition on a model, a weighting model for each mesh element, for instance, it's difficult to get an accurate model. So it's better to do a good partition, let's say, or the best possible partition with a simple model, and then at runtime you can react and you can change the partition according to measurements, right? To performance measurements on the simulation. And then what we do is, for each splitting point, we take into account all the measurements that have done for that splitting point, right? And we do a linear regression, right? So the movement of the splitting point is as complex as the partitioning problem, but if we take different, we do different movements and take different measurements, with a linear regression, we get a better robustness of the balancing process. So that's what I explained here. We consider for each splitting point, the accumulated load for until this splitting point and the accumulated time as well. And according to this, with a linear regression, we can get a smooth convergence to a proper balanced problem. A key ingredient of this method is the SFC partitioning. On each time, for each new partition, indeed what we do is generate a new partition, okay, from scratch. In fact, this can be optimized because there are some parts of the partitioning or of the SFC construction that don't need to be repeated. But in our case, we have seen that we are quite fast, so it's not necessary to optimize at the moment. It's not a critical problem. Okay, here I have a comparison with Zoltan. The problem that the mesh that we are partitioning is a 250 million elements mesh, and up to 6,000, more or less 6,000 CPU cores, and our partitioning takes about 0.1 of a second, right? So it's not a bottleneck now. It's fast, so we can use it iteratively to just improve the partition according to the linear regression. The other component of the repartitioning, it's just migrating the simulation. I don't have measurements for it here now, but it takes roughly the cost of 1 or 2 iterations, not more than that. It's some part of the code that we need to measure more in more detail and optimize. Okay. Let me show you an example of this strategy for co-execution. When we do a co-execution, that means using the CPU and the GPU at the same time. here we have two levels of heterogeneity. Heterogeneity in the hardware and as well also in the mesh, because the plane mesh here, it has different types of elements, and this always generates us problems with the balancing. Okay. The idea for doing co-execution that we use is we generate two instances of the executable, two instances of the code, one to run on GPU and one to run on CPU. Okay, and then using the multiprog option of Slurm, on each node there are some MPI processes that will use one executable and some MPI processes that will use the other one. Okay. The ones that will use the executable generated for the GPU will be offloading to the GPU, and others will remain on the host. Okay. The nice thing is that you can compile each executable with the best compilation options according to the device where you want to run. The only thing that you need is that they do the MPI calls that relate them at the same point, and that's it. Because we use the same code, just different instances of it, right? And here you can see the result. Okay, this would be an execution with 240 MPIs with 2 threads through ohms, okay, like the equivalent of OpenMPI developed in BSC. We have 2 threads of ohms per MPI process, and you see here this has been done on the I didn't say this. This is the Power 9 system in BSC. Okay, that has 2 Power 9 CPUs and 4 Volta GPUs per node. Right here we were using 12 nodes, and with the initial partition not optimized, just the same load per MPI process. Of course, the MPI processor running on the CPU cores take more time than the ones running on the GPU, right? But of course, and we can see imbalance between the MPI processor running on the CPU cores, and imbalance also as well on the CPU, on the MPI processor running on the GPUs. After this balancing process, iterative balancing process, I will show you some more details on it. We had this result is the blue line. Okay, that is the balance partition for co-execution. Okay, compared to the black line, which is a balance partition for execution only on the GPU, the difference is 23%, more or less. 23%, which is a key equivalent of, okay, if the node has 4 GPUs, but doing co-execution and using the host, it's equivalent to have an additional GPU. So it's not negligible, the performance of the host. So it makes sense to use all the nodes at the same time. More details on this. This is the different steps of the load balancing process for the CPU alone and for the co-execution. Okay, for the CPU alone, we see that the average time is constant because all the processes are running on the same type of device. But for the GPU, the co-execution, the average time, okay, decreases while we are loading more or putting more mesh elements in the GPUs, because those are faster. Okay, that's what we expect. So the imbalance that can be evaluated as the maximum time divided by the average time, or the measure of that. Okay, in both cases we get this reduction of the imbalance. In the CPU case, particularly on the Power 9 systems, what we saw is that from a certain point here, this mesh repartitioning strategy has no sense, because we are not getting better partitions from a certain point. And this is because this is the imbalance at that point comes from hardware noise, from variability on the performance of the hardware. Okay, here is where DLV, that is not used in this example, can come and help. And we are kind of giving to DLV a perfect problem to solve it very easily. Okay, because we only have some few MPIs, mostly probably on different nodes, that have some additional cost because of noise. Okay. If I measure it in terms of outliers, that I consider outlier the MPI process that are more than 1% far from the average, we see how at a certain point the outliers that just keep fluctuating. You cannot do, doesn't make sense to keep migrating mesh elements through the between MPI processes. An interesting thing is that these outliers, when you here I am comparing a pure MPI execution with a MPI plus OMS execution. Okay, we are using the same resources here, and if we consider the average time with a pure MPI execution, it's faster. It's faster. Okay, because this part of the code that I am measuring is only the assembly part, it has no communications. Okay, with a pure MPI communication. Pure MPI execution, the time is faster, but it's resilient to hardware noise. When we are using two threads per MPI process, the hardware when there is one of the two cores that gets slower for some reason, the other can help. So you have this flexibility, and that's why at the end, in terms of load balancing, it's better to use a mix, a hybrid strategy, MPI plus OpenMP or OMS, right? Although the average time is better with pure MPI, but the maximum, that is the one that is really important, it's always worse in general. Okay, so this is again the conclusion that we got here with this infrastructure, that we could get a relevant speed up by doing co-execution. Well, that's all. This is a complementary mechanism to the node level strategies that that Marta has shown, and yeah, the critical components are the SFC-based mesh partitioner, the linear regression strategy that gives us robustness to outlier measurements, and that's almost all. Like as next steps, the SFC-based mesh partitioner will be delivered as an open source library within another project. But well, if someone is interested, can write me an email, and as soon as it is ready, I can provide the link.